Hey class, and welcome back to the second part of chapter 6. Sorry, my wife is laughing. She's I had to hit record, and then it starts a countdown, and she just started talking to me right after I had done it. And now she wants me to start over, but I'm keeping it because this is more fun. Anyway, so we're continuing chapter 6. In the last video, right, we talked about an introduction to what is work and what is energy, and then now we're going to continue that to talk about another form of energy. We focused on kinetic energy in the last video. We'll now talk about potential energy, looking at the energy that anything in a gravitational field. So, I have my calculator here. The fact that it's some distance above the ground, it has a certain potential. Gravity has the potential to pull on it. If I let it go, that potential will turn into kinetic as it begins to move. And so we're going to really kind of reconceptualize energy by kind of putting things in categories, which we were introduced to last video when we talked about the different forms of energy. We're going to talk about now gravitational potential energy in particular and look at how it relates to kinetic energy and how it relates to work, putting all those together in conservation of energy. So as we do that, though, we first need to talk about and define something known as conservative and non-conservative forces so we can better understand what type of quantities can be dealt with in terms of potential energy and what type of physical forces should be dealt with in terms of work. So that's where we're going to go and start from right now. So there's really kind of two ways that you can define or think about the definition of a conservative force. The first is to understand that a force is conservative when and if the work it does on a moving object is independent of the path it takes between its initial and final position. So if you remember back in chapter 7, we talked about how the work done by gravity is independent of the path. It doesn't matter if you move straight down or if you move at an angle gently down to the same height. If your change in vertical height is the same, then the work done by gravity is going to be the same. So it is independent of path. So gravity would be one example of a conservative force. The second way to define a conservative force or to conceptualize it is a force is conservative when it does no work on an object around a closed path, meaning you start at some location, you can do whatever you want, but if you return to that exact same starting location, if there's no net work done, then you have a conservative force. So gravity, once again, can be thought about in this way. If you move down and then circled and came back up, you have no change in height, and so therefore there's no net work done by gravity. Whereas something like friction, let's say we're taking my phone here and sliding it down my hand, and then it's getting slid back up. Friction's going to do negative work in both cases, and so friction is not a conservative force because the total overall work done by friction is not zero. It's negative in both directions, and so you have an overall negative work done by friction. So again, just to make sure you understand these, if you think about an object moving from some height h initial to some height h final, and if we don't care about the path that it takes, if the work done is the same in either situation, then that's one way to know that you have a conservative force. And so as you can see, gravity is one example of a conservative force. And then here's just kind of a visual for the second definition of a conservative force, where you have an object, if it goes around an entire closed loop and ends back at the same location that it started from, then it would be doing, if it does no net work during that time, then it would be a conservative force. Again, gravity is an example of a conservative force, whereas something like friction is not. And so here's just to show you, friction would be considered a non-conservative force because no matter what direction you're moving, it's always doing negative work, and so you can't get a situation where you end up with zero net work. All right, so here's a list, just kind of a table to kind of show you some conservative and some non-conservative forces to help you understand some examples. So things like the gravitational force, the elastic spring force, stuff that we've already talked about a little bit. Electric forces due to electric fields, which we'll get to in second semester physics. Those are all examples of conservative forces, whereas examples of non-conservative forces are things like friction, air resistance, tension, normal force, and things like a propulsion force from a rocket or in a car. Those are examples of non-conservative forces. So why do we care? Why am I talking to you about conservative forces? This sounds fun and everything, but what's the point? Well, what we see and what we observe, if the work done by an object is independent of its path, and if it's zero in a closed system, then what that means, because it's a conservative force, you can actually think about the work done by that force, not necessarily in terms of just a typical work done by any force, but you can actually think of it in terms of what we're going to call potential energy, what we introduced in the last chapter as potential energy. So since gravity is one example of a conservative force, we can define gravitational potential energy. Gravitational potential energy is the potential that gravity has to do work on an object. And since it's conservative, that energy is always going to be there because we know it has the potential to do that work at all times. And so the way that we define potential energy is just equal to mass multiplied by gravity multiplied by the height that your object has at a given point in time. All right? So if you notice, what is work? Work done by gravity, we've already defined back in the last chapter, mgh initial minus mgh final. So if we're saying that potential energy is mgh, then work is really just the negative change in potential energy. So as you can see here, we can observe that the work done by gravity, since it's independent of path, the gravitational potential energy is all we really have to worry about or care about. The gravitational potential energy as it changes from some initial height, y1, to some final height, y2. Now the second example that we're going to use for now in terms of potential energy, we'll add others, especially next semester and as you continue on in your careers. But the other one that we already have talked about a little bit is defining what we call elastic potential energy, which is the potential for some spring or rubber band or something along those lines, the potential those have to do work. All right, so the way that we define potential energy for a spring is that the potential energy is just going to be equal to 1/2 kx squared. Again, potential energy, you'll observe, is just going to be the negative of the work done by a spring as it moves. Okay, so people get confused. What's this business about, work being equal to the negative of potential energy, right? Why are conservative forces the negative of potential energy? Well, what that means is we're really just talking about the amount of potential it has for gravity to do work on it. So if I have a ball at some height here, it has a certain amount of potential energy. Okay, if I let it go and it falls, then gravity has done work on it by taking away that potential energy to do work. That taking away is the negative sign. All right, so the potential energy, as it changes, you're losing potential energy. Where is that potential energy going? Well, it's going to do work on your system, in this case, on my ball. And the same thing is with a spring. If you pull back a spring, it's locked and ready to go in like a Nerf gun or something like that. Well, there's potential there for that spring to do work. If you release it, that potential energy is going to be taken by the spring to do work and be added to your system. All right, so again, that's where that negative sign comes in. One other thing I just want to make really clear to you, I don't think this is in the PowerPoint slide, so I'm just going to jot it down on the board here. But keep in mind, you're going to see potential energy expressed a couple different ways throughout your careers. You'll see in my PowerPoint slide, I'm using PE to represent potential energy. That's a very common way to represent it. But you'll also see the letter U written to represent potential energy as well. So don't get confused with that. So like gravitational potential energy could be written PE with a subscript G, or it could be written U with a subscript G. Elastic potential energy could be PEL for elastic, or U with an EL at the end. Okay, so don't get too confused. Kinetic energy, similar kind of thing. You'll see KE or just capital K. Both of those represent kinetic energy. All right, cool. So anyway, what I have here is I want to now expand the work energy theorem to incorporate potential energy to give us a really nice, clean, crisp way of working with, writing, and thinking about overall energy for a system. So remember, the work energy theorem tells us that work is equal to the change in kinetic energy, right? And now we can think about work in terms of two different types of work. There's conservative work and there's non-conservative work. And since conservative work can be thought of in terms of potential energy, we're going to replace the work done by conservative work with negative change in potential energy. All right? So now, be careful. Some people start to double count things like gravity. They put it in work and they put it in potential energy. No, we're taking away this idea of work done by conservative forces and replacing it with potential energy to make our lives easier and more accurate in a lot of ways, okay? So the work is change in kinetic energy, and the work done by conservative forces is negative change in potential energy. And then the W with the NC as a subscript, that's just work done by non-conservative forces. So that's kind of the catch-all for everything else that's not kinetic or potential energy. So if we plug all these things in to our equation here, the work energy theorem, we start to get a new way of looking at, writing, and thinking about energy. So change in kinetic energy equals negative change in potential energy plus any work done by non-conservative forces, right? And so what this is telling us is that we really can think of the work energy theorem in a new way, that work being done by any non-conservative forces is just equal to the overall change in energy of your system. That's change in kinetic and or change in potential energies. All right, so work done by non-conservative forces is equal to the total overall change. Because what this is telling us is we can have work that's being taken up by giving potential energy to something, right? So work can either cause something to move, giving it kinetic energy, or positive work can give something potential energy. So if you take a ball and you throw it straight up, all right, you're doing work to get it going, but as it moves up, it's slowing down, right? Where's that work that you did go? Well, it's going into gravitational potential energy on the ball that you threw upward. All right, so this is the overall work energy theorem. I'm going to rearrange the terms here into a way that I find most useful for problem solving and that most students tend to find useful as well. So if we rewrite this idea of work by non-conservative forces equals total change in energy, we can replace change in kinetic energy with KE final minus KE initial, and we can replace change in potential energy with PE final minus PE initial. And then if we reorganize our terms a little bit, putting the initials and finals together, moving the initials to the other side of our equation, you get an equation that tells you your total initial energy plus any work done by non-conservative forces equals your total final energy. All right? So again, this is telling us that whatever energy we start with plus any work done by non-conservative forces gives us whatever energy we end up with. All right, and if you have no work done by non-conservative forces, then energy is conserved, right? Conservation of energy for a closed system. So this formulation of conservation of energy is the one I recommend that you start with, either this writing of it or the one down here, okay? But always, every time you're going to do a work energy problem, start here. What energy do I have to start with? What energy do I end up with, and what work is being done by non-conservative forces? Okay, so always start here. Do you have initial potential energy? Do you have initial kinetic energy? Do you have work being done by non-conservative forces? Do you have final kinetic energy? Do you have final potential energy? Every work energy problem that you do, I want to see this equation written at the very top as your starting point, and then substituting in from there. Okay, if you stay organized, work energy problems are some of the easiest you're going to tackle throughout the semester. If you're disorganized, though, oh boy, howdy, it's going to be a headache, okay? All right, so again, this brings us back to where we really started at the beginning of Chapter 7, which is with the principle of conservation of energy. Meaning, if you're in a closed system, so a system that's free of any non-conservative forces doing work, then total energy will always be conserved. Whatever energy you start with will equal the energy that you end up with. So just to kind of give you, some sort of examples, some conceptual, we'll do numerical examples in future videos, but for now, just kind of some conceptual ideas. If you think about two people in a bobsled, all right, they're just first getting their kind of experience with the bobsled, so they're not doing the running start yet. But instead, they start from rest and just barely lean, and they start going faster and faster as they go down. Well, what makes them go faster and faster? Well, they have some initial potential energy. So if we had an ideal system where there's no friction or anything going on for this bobsled, then what would happen is they would start with some amount of initial potential energy, in this case 600,000 joules, and as they moved down, since their height decreases, their gravitational potential energy decreases, but due to conservation of energy, the exact amount by which it decreases is the amount by which the kinetic energy would increase. They move down a little further, their potential energy decreases more, but yet their kinetic energy increases more, and then when they get to the bottom, they're out of potential energy and it has all become kinetic energy. So you can just see sort of the process of how that works. All right, so kind of a conceptual example. You could actually do some numerical calculations with this as well, but we're just going to talk about it conceptually at the moment. So imagine you had some large crate. You slide it up a ramp. All right, let's say it's a 30-degree angle. Okay, you do a quick calculation in your head. You're like, all right, I know it needs to get to the top of this ramp, so I know it needs to have a certain amount of potential energy when it gets to the top. If I want it to just barely stop, I want it to have no kinetic energy at the end, so I must push it with a certain speed to get it exactly to the top. You do all this mental math because you're helping some friends move and you love physics, who doesn't? And you find that you must push with an initial velocity of 5 meters per second. You push it with that and you find out, oh man, bummer, it didn't make it all the way to the top. It only made it 1.6 meters up. What's the deal? Well, what do you think? Why did it not make up all the way? Well, as the kind of question at the top implies, and you probably figured out, you would have friction at play, and the friction would slow it down, taking away energy. So while you calculated the exact amount of energy needed to get it to the top, you assumed that it was frictionless. As I mentioned, there's nothing in here about friction. Another question, if it came back down to you, if you pushed it at 5 meters per second, it went up, stopped, didn't make it all the way, and then slid back down, would it be going 5 meters per second when it got back to you? Yes or no, and why? Think about it, commit. Guess what the right answer is? No, it would be going slower because friction not only would take away energy from your system on the way up, it would continue to take away energy on the way back down. And so by the time it returned to you, it would be going significantly slower than that 5 meters per second that you pushed it with. Sneaky, huh? All right, here's another conceptual example for you. So here's a kid. He starts at 0 meters per second. He's got this rope swing. He's going to swing through 90 degrees and have some final velocity here at the very bottom. All right, so again, he starts from rest up here. He swings down until he's perfectly horizontal, and then he's going to let go and plop into the river for some physics fun. All right, there's 3 forces acting on him: his weight, the tension in the rope, and air resistance. Okay. Can you use the principle of conservation of energy to calculate his final speed if you were to know this initial height and this final height? What additional information would you need to know to figure it out? Think about it for a minute. Maybe another question to think about is, what is doing work on him during this time? Which forces are doing work? What if you could ignore air resistance? Then what? Could you solve more easily at that point? So let's talk about it. If he swings through to this position, what forces are doing work on him? Well, there's definitely gravity, right? There's a change in potential energy. So whatever initial potential energy he has is turning into kinetic energy when he gets to the bottom. If we ignore air resistance, that's it. All we have is initial potential energy equals final kinetic energy. mgh up here equals 1/2 mv squared down here. Okay? Pretty neat, right? The reason for that is because we're ignoring air resistance. If we had air resistance, then we'd have to calculate the work done by it. But tension, does tension do any work? That's the part that tends to confuse people with this one. And the answer is no, because the tension is always perpendicular to the direction of motion. Remember back to chapter 7, work is only done when you have force in the direction of displacement. So in this case, if the tension has no component in the direction of your displacement, then it does no work. Interesting, right? So the last thing I want to finish up with is this example, kind of just thinking about conceptually again, what's going on with conservation of energy. This is Danny Way, a skateboarder who once did this. So pretty cool. I'm not a big skateboarder myself, but as you saw, he went and used gravitational potential energy to help him jump all the way over the Great Wall of China. So what I wanted to do, using the help of some analytics that Dr. Hamilton has done on this exact problem, is apply conservation of energy to this situation. So let's look. Here's kind of a picture of the ramp, the Great Wall of China, where Danny Way jumped, and then the landing ramp as well, and we saw him go up and come back down. All right, so you can look at this, and Dr. Hamilton went through this pixel by pixel to figure out approximate sizes of different things, radiuses of curvature for his different jumps and whatnot, starting heights at different locations, and so on. And based on this information, you can use conservation of energy to analyze what's going on here. So this here is a plot of his potential energy as a function of his distance. So as you can see, when he starts up here, he's at his highest height. He has the most potential energy because he's at the highest location up here at Y1. All right. As he moved down in height, his potential energy decreased, right? And what would happen then? Well, his kinetic energy would increase. He'd be going faster as he moved down. Then as he jumped and went back up, he's gaining more gravitational potential energy, meaning he's slowing down and decreasing his kinetic energy. And then as he comes back down, he gets more and more and more and more kinetic energy. And then it returns to potential energy as he goes up off of his last jump. So a cool thing to think about, if you want to think about conservation of energy, you can use this graph to sort of represent conservation of energy. So what on this graph represents kinetic energy? I just told you what the potential energy is this distance from the bottom up here, right? That's your y-axis, is your potential energy. What is the kinetic energy? Is it on the graph? Well, remember, conservation of energy tells us total energy is kinetic energy plus potential energy, right? So keeping that in mind, what do you think? Well, if we think about conservation of energy, if whatever energy he started with, all that potential energy he started with, that's going to be constant, right? That's his total energy the entire time. So if we think about that initial energy as the total energy, then what that means is as he moves down and decreases his potential energy, the kinetic energy would be just the difference between his potential energy now and that starting energy, right? Because the total energy stays the same the whole time. So if potential goes down, kinetic must increase. So this is sort of a graphical representation of his kinetic energy versus his potential energy. And if you were to go back and watch the video again, what you would see is he gains in speed down to here. He gets going faster and faster, more kinetic energy. As he jumps, his overall speed slows down some, but he doesn't stop here, right? He still has x velocity, so therefore he still has some kinetic energy there. And then as he moves down, he gets going faster and faster and faster until he goes fastest right here when his potential energy is lowest, and then as he jumps, he'd go back up. Now, all of this is assuming conservation of energy. If we included friction and air resistance, then we'd probably have a gradual decrease in our overall energy as he continued to move. So that really wraps up the concepts from Chapter 8. It's really just an addition to Chapter 7, right? But I'm going to do a couple problem-solving examples for you all in separate videos. So check those out next, and let me know if you have any questions.